Hi, welcome back. In this video, we're going to continue our discussion on work, energy, and potential. Let's get started. First, I want to introduce to you the concept of an electric dipole. So electric dipole, which is in the title there. Electric dipole is a pair of 2-point charges of equal magnitude and opposite sign, and they're separated by a small distance. So I'm just going to draw an electric dipole on an XYZ coordinate system. And I'm going to have that dipole, for convenience, be situated on the z-axis. So they are, again, two equal and opposite charges, so plus q and minus q, separated by a small distance, d, like that. And I'll say more about small distance in a little bit. And then we're going to consider, or what it means to have a small distance. And then we're going to consider the electric field point, at a point somewhere over here out in space. And I'm going to draw these vectors, one from the origin and the other two from the charges, going to our point in space at which we will consider the electric field. I'm going to label this vector r1, this distance vector r2, and this position vector just will be r. Okay, so this is an electric dipole situation, and I've exaggerated the distance d. Normally d would be very small, like on the atomic level, and p then is much larger, like distances that we can see, that we can visualize, like meters or something. And this situation, this electric dipole situation, arises in materials, particularly in the operation of transistors, junction transistors and FETs. You'll have an electric dipole, and then so that separating distance is on the order of atoms, and then the field point is something like on the printed circuit board, so like centimeters maybe. So P is much larger than D, which I'm not showing in this figure. It's just so I can show some details. And speaking of those details, we are going to define this angle here that the axis of the dipole, which is the z-axis, makes with our position vector to the electric field. We're going to call that theta. All right, and we're going to find that electric field by first finding the potential at P. Remember, they're related, so we can find the potential at P. We're going to call V plus the potential at P due to Q plus. So that would be Q over 4 pi epsilon 0 R1, where R1 is the magnitude of vector R1, and here we're assuming that V at infinity is our reference point. V at infinity would be 0 potential. And similarly, V minus, or the potential due to the minus charge, is negative Q over 4 pi epsilon 0 R2, where R2 is the magnitude of vector R2. Now, potential differences obey superposition just like electric fields do. So the total potential difference at point P is the sum of those two things, Q over 4 pi epsilon 0 times R1 minus 1 over R2, like this. And then getting a common denominator, we can actually write that as Q over 4 pi epsilon 0 times R2 minus R1 over R1 times R2, the common denominator there of R1 times R2. Now, if P lies in what's called the far zone, and this is what I made reference to earlier, we're going to call this the far zone, meaning again that R, which is the magnitude of vector R, the position vector, is much larger than distance D. Then we can make some approximations. And regarding these approximations, if you don't follow what I'm about to say next, that's okay. A little bit of this is some hand waving. I don't want to show the geometric details. But you can imagine if P is far away, then R1 and R2 are approximately parallel. And in that case, the difference between the lengths of R1 and R2 is like this distance here. And that distance, it turns out, is about d times cosine of theta. And as P gets further and further away from the origin, R1, R, and R2 approximately have the same length. And so, and that length being R. So R1 is about on the order of R, R2 is about on the order of R. That's all to say the following. R2 minus R1 is d cosine theta in an order of approximation, and R2 times R1 is about R squared, where R is the length of vector R. Again, if you didn't follow that, that's okay. It's not crucial to electromagnetics. What you do need to know is the result. That makes the potential then, due to this electric dipole, as Q over 4 pi epsilon 0 times d cosine theta over R squared. Now, the numerator looks a lot like a dot product, where we have a scalar times a cosine of an angle, right? And so let's work a dot product in here. And what we're going to do is define a vector d, a distance vector, which is the separating distance times a unit vector along this axis, the dipole axis. So that in this case that happens to be AZ. But in general it's along the dipole axis, and it goes from, and this is important, from negative, the negative end of the dipole, to positive, the positive end of the dipole. Right? So that's how we're defining this distance vector now, related to the dipole. That's a property of the dipole. Then we can see that d cosine of theta is d, vector d, dotted with a unit vector in the r direction. So here's the r direction, here's AR. So if I want the angle in between the dipole distance, d, and AR, theta, they're related by this, going to the definition of the dot product. Now we're going to define the dipole moment as a vector P, which is Q, the charge of the dipole, right, the positive charge, times the separating distance. So that's a property of just the dipole itself. That's the dipole moment. And then I can rearrange or rework the potential due to the dipole as being the dipole moment dotted with AR, nice, right, over 4 pi epsilon 0 R squared. So the dipole moment allows us to conveniently express the potential due to the dipole as a dot product. That's cool. That's nice. Now, just one little caveat here. If the dipole is not centered about the origin, so in general, we would say that the potential is P dot R minus R prime, where R prime is the center, is the position vector of the center of the dipole, over 4 pi epsilon 0 times the magnitude of that distance cubed. Right? So we saw something similar when we were applying Coulomb's law, how you can convert the unit vector, right, to this. Okay, almost finished with the dipole. There are a couple more things that I want to say. So I'll come up top here. Remember that the electric field, so we haven't gotten the electric field yet of the dipole. We've got the potential. Remember that the electric field and the potential are related like that. Sometimes it's easier to find the electric field indirectly through the potential because the potential is a scalar, and then we just need to take the negative gradient of that scalar field. So in this case, in spherical coordinates, this is what the electric field would reduce to. I don't have to worry about the phi direction because there is no phi in my expression for potential. There's an r and there's a theta. So when I carry that out, r 1 over r squared is like r to the minus 2, and so I take the partial derivative and that becomes negative over r3, or r cubed that is, and so the negative cancels with that negative, and so this gives me, I'll let you work that out on your own, that gives me this r cubed ar, and then when I take the derivative of versus cosine, that turns into a negative sign. That negative cancels with that sign, or that negative, and so what I end up getting here is qd sine theta over 4 pi epsilon 0 r cubed in the theta direction. And then using the dipole moment, which is q times d, right? Here's q and here's d. We can write this as p. So I'll factor out the q and the d, and I'll factor out a 4 pi epsilon 0 r cubed. Factor all that out, we're left with twice the cosine of theta in the r direction plus the sine of theta in the theta direction. And p here, in keeping with the notation, p is the magnitude of the dipole moment. So the magnitude of this dipole moment is q times d without the arrow. And so you see here we have q and d without the arrow. All right, so that's the electric dipole. And now I want to move on to equipotential lines, but you'll see that I do have a dipole over here in the figure. So we're gonna tie in equipotential lines with the dipole. So now let's start to consider the figures, and I want to start with this guy on the top right. Electric flux lines are imaginary paths whose directions are in the direction of the electric field, or the electric flux density, since they're parallel with one another. So in this top right figure, I've got an electric monopole, which is just one charge, and it's positive in this example. And we might ask ourselves, if I put a positive test charge next to this monopole, which direction would it go? Well, if I put it right here, let's say, it would go this way. And if I put it right here, it would be repelled from the monopole, and it would go this way. And we've worked through this. We know that the electric field goes radially outward. So that's why the black arrows point radially outward. And we would call those black arrows electric flux lines. Again, they're imaginary paths whose directions are in the direction of the electric field, or the electric flux density. Let's not worry about the green circles for right now. Now, if we go to the electric dipole, which is in the top left, you'll see something similar. You'll see these electric flux lines, and they're in the direction of the E field. And here's my positive charge on the left, and here's my negative charge on the right. So, you know, if I was able to put a test charge there, positive test charge, we know that it's repelled from the positive charge, and it would go right, almost directly to the negative charge along this path. Similarly, if I was to put a charge here, positive, it would be repelled from this positive charge, but it would be attracted to this one, and so in such a way as it would take this path. You can even kind of picture the animation in your head. Now, if we put a charge, let's say over here, right here, it's off axis slightly, and so it's going to be mostly repelled by Q, and eventually, so it's going to go off the screen, and it's going to come all the way back around this way, and eventually it'll make its way to the negative Q. So it takes that path. So again, those are the electric flux lines for that electric dipole that we just discussed. Now really what I want to get to is the equipotential lines. An equipotential line is a locus or a collection of points whose potentials in space, potentials, are equal. So since the gradient, remember, is always normal to the field, perpendicular, and E is the negative gradient of potential, equipotential lines are always normal to E everywhere in space. Okay, so now let's look at this electric monopole again, top right. I've got three equal potential surfaces drawn as circles in green, labeled V1, V2, V3. Let's say V1. Let's say you put a charge on V1, and it has a certain potential at V1. Well, if we moved it to say here, and we stayed, I guess it doesn't matter, but if we now put it here, it doesn't matter the path taken, but if we now put it here, it has the same potential there, and I've labeled that potential V1. And again, the equipotential surfaces are perpendicular to the field. So you'll see here's a perpendicular, perpendicular, perpendicular. They're always perpendicular, right? Now, separately then, maybe we instead place a charge on V2. Anywhere we place it on V2, it will have the same potential. So it's the collection of points. So if we put it here, if we put it here, if we put it here, if we put the charge there, if we put the charge anywhere along that curve or that circle, it will have potential V2. And you can make a similar argument for V3. And I'm going to ask the question eventually, which is the higher potential, V1, V2, or V3? So maybe you want to think about that as we go through this. Also, same thing over here for the electric dipole, but let's look at the bottom left figure. In the bottom left figure, the solid red lines are the electric field or the electric flux lines. Perpendicular to that then are the green dashed lines that are the equipotential lines. So again, they're perpendicular everywhere. You see that? Those are the equipotential lines. And you can keep drawing those if you want. But if I were to put a charge, let's say here, that charge has a certain potential. And if I move it anywhere along the green line, it has the same potential measured in volts. Anywhere along that line, same potential. And there's nothing particularly interesting about the line that I chose. I could have made the same argument with any green dashed line. Now let's get work into this. Recall that potential is normalized work. It's the work per charge. It takes then no work or no force to push a charge along an equipotential line. So let's consider the gravitational field right now, because we have more experience with gravitational fields. So let's consider a hockey puck, and the reason I consider a hockey puck on the ice is because I don't want to talk about friction, because friction is not part of the gravitational field. There's no friction of a charge moving in an electric field, so let's not talk about friction. So absent friction, it takes no work to push a hockey puck along the surface of the ice, right? You can give it an initial push, but then after that, it'll go on forever unless another force acts on it. And that's because the gravitational field points downward. And notice then our equipotential surface is perpendicular to the gravitational field, just like in the electric field. This makes sense from what you know in physics, right? When you talked about potential energy, you just said, oh, let's let y equal 0 here. Anywhere along this horizontal, the object has the same potential energy. All right, let's look at the electric monopole again. And I've got these things labeled V1, V2, V3. Now, which potential line is the largest potential? Think about it. And remember, the potential is the amount of work required to bring a positive test charge from a reference point to that line. So here's a positive charge. It's if I'm bringing it from out here from minus infinity into the space, this thing is going to oppose that. It's going to try to keep me from doing that. So is it easier? Does it require less work to get it to V3? It does. It requires less work to bring it to V3, even more work to bring it to V2, and even more work to bring it to V1. Therefore, V1 has the largest potential, V2, and then V3. This would be like in the gravitational field, having a mass like this. Okay, here's V1. Here's V2, right? These are distances. Distance 1, distance 2, distance 3. I guess you don't use V in gravitational field. But here's the gravitational field. So does it require more work to lift the mass this high, or this high? Well, the longer you go against the field, the more potential you're giving it, right? Same thing here. The more you go against the field, so going up to V1, the more potential it has, the more work you've had to do that. Awesome. So now we've talked about work, we've talked about equipotential lines. One last thing kind of to shore up all of this conversation about work and energy is actually the energy that an electrostatic system would be carrying at any point. So let's take a look at the energy of an electrostatic system.